Hi guys, we are looking at the section 2.2 homework in this video, and it's unfortunately a very calculator dependent section in trying to develop these concepts of limits. So as I show you my work, I'll also show the calculator as well. Now in this first one, it's having me look at the limit as x approaches 7. And I would prefer you write the limit notation like this as opposed to how they had to write it in Achieve. Something about their type font didn't allow the x approaches 7 to go under the limit. That's unusual for it to be written like that. But we have the limit as x approaches 7 of x cubed minus 343 over x squared minus 49. Now, clearly you can't just plug a 7 into this function. 7 cubed is 343. So you'd have 343 minus 343 over 49 minus 49, which we know that's just going to be 0 divided by 0. So this function is undefined at 7, but that has nothing to do with whether there's a limit or not at 7. The limit as x approaches 7, it's not specifically asking what f of 7 is, but it's asking what one y value, or if there is one y value, does this approach as we approach 7 from the left or 7 from the right. So what is f of 6.9? What is f of 6.99? What is f of 6.999? What is f of 7.1, 7.01, 7.001? Is it approaching some y value? Now, they gave me a table of values to plug in. I'll go ahead and maximize my screen and show how that worked out. So what I did here for the first problem, we had x cubed minus 343. I'll go into the y equals screen, clear that out. I think it's probably better, especially if you're on a calculator that has the fraction key, you just hit alpha y equals and do the fraction. Otherwise, just remember to keep parentheses around your numerator and parentheses around your denominator. It would have to be there. This just keeps us from needing to worry about that as much. We have x cubed minus 343, and we're dividing that by x squared minus 49. Okay, so now in order to set your table up to be able to correctly answer the values that they want for this problem, they ask these specific x values as x approaches 7 from the right and as x approaches 7 from the left. Well, most people, whenever they have their table set up, comes from algebra classes. Most algebra teachers want you to have the x values automatically given. So you can see when x is 1, 2, 3, 4, 5, 6, and you can just keep on scrolling through there. Never is that going to be helpful again. You want to be able to input the x component and have it give you the y component. So when you go second table setup, that independent needs to be on ask, and you'll never want to move away from that ever again. So now that I have it set up that way, I'll go to my table. Now, you can see I already have some values in there, and they're not important for this problem. The clear button doesn't work, but the delete key will. It just deletes them one at a time. So I just delete all those out. Now I enter in what I need. I have the 7.002. I have the 7.001, the 7.3 zeros and a 5, and the 7.3 zeros and a 1. Now, unfortunately, a lot of students will just look at that and think, well, there's your answers. No, it's not. You need to scroll over to each of those in order to get the more exact value. So that first value, what is f of 7.002? Well, it's 10.5015 0.00714. Now, sometimes you need to put that entire decimal out there so you can see what's happening to this function and see what it's approaching. Written really didn't absolutely need it in this case, but it's never a bad thing to be more accurate than what you need. So I went ahead and put out all of the decimal places for all of these values, the 7.002, the 7.001, the 7.3 .0005 and the 7.0001. Now, I'm particularly interested in the second and fourth entry. What happened when I got 10 times closer to 7 from this value to this value? And I can say, well, this is 5.007, this is 5.0007. I can already see a pattern here, guys. I know that if I went to 7.00001, 4 zeros in a 1, it's going to add yet another 0 in between this 5 and this 7. So when there's 2 zeros here, notice there's 2 zeros here. When there's 3 zeros here, there's 3 zeros here. The pattern here is going to be, well, then if you have 7.4 zeros in a 1, you're going to have 10.5 and then 4 zeros in a 7. So what is that number approaching as x is getting closer and closer and closer to 7 on the right? And I can easily see, well, the limit as, and this is the notation I want you to use, this means the limit as x approaches 7 on the right of this function clearly is approaching 10.5. Sometimes students mistakenly want to put one of these values. Please remember, that's not the value it's approaching. That is just one y value at a specific x value. The y value that it's approaching as x gets closer and closer and closer to 7 is a y value of 10.5. Now, you can see that as x approaches on the left-hand side as well. I'll go ahead and show you on the calculator here. On the calculator, I would just go in, well, I'm already on the table, so second table. Don't want to see the graph. Go away, graph. Stop. Go back to the table, and I'll go over to the x values. Now, on my calculator, I don't have enough resolution to enter in all of these x values. If you have one of the newer calculators, you will have the resolution. I actually have to use the older calculator for these videos because my newer calculator has a shiny screen on it, and it does not do well in these videos. So I'm going old school retro TI-84s instead of the newer nice flat ones. This one's one of the old thick ones. 6.999, 6.39s and a 5, and 6.9999. I apologize, guys, if you hear a dog barking in the background. My neighbor's dog is having a fit. When you look at this here, you can say, well, okay, please notice when you have 6.998, your y value is 10.4985. So what we're expecting to see is as this x value gets closer to 7, this y value is going to get closer to 10.5. And you can see, yeah, that happens. It goes from 4.4985 to 4.4992. Now, I only did these increments just because that's what was asked. Whenever I do increments on my own, I always go in terms of like powers of 10, like 7.001, and then 10 times closer, 7.0001. I would have gone 6.9999 and then 6.49s. That's when you usually see the patterns. Please notice, from the second one to the fourth one, I can see the pattern. When I have 3 9s, I have 10.49925. What about when I have 6.49s? 10.4999, it added another 9 between the 4 and the 2. And please note that 4 would round up to a 5, so it's still essentially the same number after the 9. So I can see that what this is going to give me is the 10.4999. That's going to be approaching a value of 10.5. And so now I can see whether the limit is approaching 7 from the right or from the left, that y value is approaching 10.5. So now I can see, okay, I have the limit for this first problem. The second one, and I'll just keep this full screen on Achieve, asked me to look at this problem, the limit as y approaches 6 of this rational function with respect to y, and it asks me to find the right and the left-hand limit using these values. Okay, so I'll go into the calculator real quick, And I won't do all of these with the calculator. Once you see how to do a few on the calculator, then I'll just go through my solutions on the others. But for this one, I would go in alpha y equals, enter in my function. Of course, variables are arbitrary. I can go ahead and just call it x since that's easier to type in. X squared minus 5x minus 6. And my denominator is going to be x squared minus 2x. And then I have minus 24. Okay, so I have my function entered in. I want to find the left and right hand limit. All right, I go to my table. I have values that are not helpful. I delete those values off. Then I go in 6.002, 6.001, 6.3 zeros, and a 5, and 6.3 zeros, whoa, 3 zeros, John, not 4, and a 1. Boom. So now I can go over here and I'll see the y values. You see my first y value, the 7.3059988. Now, these others I only did, well, actually, the ones I would have done myself are the second one and the fourth one. Personally, I really don't like the fact that they ask you the first and third value. That doesn't really help establish a pattern. If I just asked you this second one and this fourth one, and I said, can you see a pattern? You would hopefully say, well, yeah, I can see a pattern. If you go 1/1000th of a distance away to 1/10,000th of a distance away, you go from a number of 0.7 and 3 zeros, 29997, to 0.7 and 4 zeros, 29997. It also added another 9 between this 2 and 7. So I can see, definitely I can see a pattern. So what's going to happen as you put more and more zeros before that 1? Well, this number is going to approach just 0.7. It's going to be 0.7 with a billion zeros after it. Well, that limiting value is a y value of 0.7. So we can say as y approaches 6, and notice all of these values are greater than 6, so that's as y approaches 6 from the right of this function in terms of y, we can just say, hey, that's got to be 0.7. Now, if I try to find the left-hand limit, and again, my screen resolution will keep me from showing them all on the same screen, so I'll come up here and say 5.998. Now, again, I really don't like that they ask you the first and third one here, but I had to do it because they did on their assignment there. Really, if I were doing this myself, I would only do the second and fourth one. That's where you see the good limit starting to exist. So now, when I'm looking at this, I can say, well, f of 5.998 gave me 0.699399987. Okay, now, what if I go half the distance? Well, as I cut the distance from the value to 6, this value is supposed to get closer to 7. Well, clearly it does. But more clearly, you should be able to see the pattern when you go from 1/1000th of a distance away from 6 to 1/10,000th of a distance away from 6, from 5.999 to 5.9999. Please notice what happened to our y value. You had 0.639s in a 6. Now you have 0.649s in a 6. So you can say, well, then this number is going to be approaching 0.699999999. And then what one y value is that 0.6999999 approaching? Well, it's approaching a y value of 0.7. So you can say whether we approach from the right or the left, the y value is approaching 0.7. Therefore, we can say the overall limit is approaching 0.7. Now, remember from the notes, that's the only time you can say an overall limit is approaching one number is if the right and the left-hand limit both go to that number, then the overall limit goes to that number. The next one here gave me a logarithmic function multiplying an algebraic function. I'll go ahead and show that real quick here. We go into y equals, I'll clear that out and say it's 3x natural log of x squared plus 5. Then I'll go to my table, delete those values out. The values that we needed for this problem were 1, 0.5, 0.1, 0.05, 0.01, 0.001, and 0.0005. So I entered those values in that they asked me to, and let me just confirm just for a second that those are all the values that they asked in this problem. I'm not particularly, yeah, those are the values that they asked for. I'm not particularly fond of the values that they asked for in this problem because, yes, the y values are getting smaller and smaller and smaller, but I wouldn't say that this is conclusive evidence right now that the y value is approaching 0. That's what they're wanting you to conclude from this. The closer the x value gets to 0, and anytime you have a logarithmic function in there, you have to approach 0 from the right. The function doesn't exist to the left of 0. So we can say, well, I have to approach 0 from the right, and when I do, that y value is getting smaller and smaller and smaller. Really, in order to see it, you might even want to go to, instead of 0.0005, you might want to go 0.0001. And notice the y value at that point, the calculator, it's so small the calculator had to put it in scientific notation. It's 0.0004828. And then if you really wanted to see it, you could go what about 1, 2, 3, 4 zeros and a 1. That y value, again, it's so small, it's putting it in even smaller scientific notation. This is more clear evidence that, yeah, of course, the y value is approaching 0. So as x approaches 0, we know the y value, this function's value, is also approaching 0. Now, number 4 was a really strange problem here. Didn't like it a bit. Notice it's just saying evaluate the limit as x approaches 25 of x. Of course, the answer is 25. There's no work to show in that one. Anytime a function exists at where its limit is going to, you just plug it in. So that's the same thing as f of 25. As x approaches 25 of just x, the y value is also approaching 25. Now, in our next one, we can't just plug it in. If you tried, it'd be the square root of 64, which is 8. Your numerator is 8 minus 8. Your denominator is 64 minus 64. So you say, well, that's 0 over 0, which is undefined, which means in this section, we solve it numerically. So I say, okay, now, did they give us a table of values? Let me check here real quick. They did not. So this table of values I came up with on my own. Now, I needed to find the limit as x approaches 64. So what I had to do, I had to establish a left-hand limit and a right-hand limit. Please notice I went 1/10 of a unit to the left of 64, 63.9, then 100th of a unit to the left of 64, then a 1,000th of a unit to the left of 64. That should establish the left-hand limit. For the right-hand limit, I went 1/10 of a unit to the right, 100th of a unit to the right, 1,000th of a unit to the right. In each of these, the number should be approaching one term. Well, notice what happened here. When I plugged in 63.9, I had 0.0625244. Okay, so if I get closer to 64, do I see some pattern in this number? And I can see, well, I can already see a pattern. From here to here, it added a 0 between the 5 and the 2. What if I go another decimal place out and get 10 times closer? I can say, well, no surprise, it'll add yet another 0. So if I hypothetically asked you, what's the y value going to be at 63.9999? You should already know that. Without going to your calculator, it's going to be 0.0625000244. Guarantee it. And so then you can say, well, what is this telling you? It's telling you that as you're approaching 64 on the left-hand side, that y value is getting closer and closer and closer to 0.0625 because it's just going to have a bunch of zeros after it. Now, is it the same thing from the right-hand side? You bet. When we go 1/10 of a unit to the right, 64.1 gives me 0.0624756. When I got 10 times closer and it was only a 100th of a unit to the right, my y value is 0.0624. And then please notice between this 4 and the 7, you have a 9. So I get 0.0624976. when I went out to 1,000th of a unit to the right, so I'm getting 10 times closer, and I can say, well, what happens is I get another 9. So this is going to be approaching a value of 0.06249999999. You can put as many 9s there as you want. What one number is that approaching? It's approaching a number of 0.0625. Glorious stuff there. Now, for the next one here, let me go back to this real quick. Number 6. Some of these, they provide a specific table for you. Others, they just want you to think of the numbers yourself. This is one of those where they just wanted us to know the numbers ourselves that work. So I was given this rational function and asked to find out what the limit as x approaches 14. Every single time that's the case, guys, I think it's very straightforward as to what you should do. I would always go 1/10th of a unit to the left, 100th of a unit to the left, 1,000th of a unit to the left, 1/10th of a unit to the right, 100th of a unit to the right, 1,000th of a unit to the right. Now, if you want to save some time, and you know that the values really get better and better as you get close, you might just want to do the 100th of a unit and the 1,000th of a unit. 100th of a unit and 1,000th, and usually you can go ahead and see a pattern just from those two terms. So even if I didn't do that 13.9 here and I just did these two, could I establish a pattern? What's happening from this term to this term? Well, they're both 1.0667, 1.0660. Well, it's 1.066, 1.066, and then I have another 6 before this 7. So then I can say, I can already see a pattern. Each time it's just going to add an additional 6 between this 6 and this 7. Notice I had 6, 7, and then 6, 6, 7, and then 6, 6, 6, 7. So I can say, then what number is this approaching? It's approaching 1.06 repeating is what it's approaching. Now, they wanted an answer to 3 decimal places, which to 3 decimal places, this is just going to be 1.067. Now, as we approach from the right, the same thing should be established. If I just look at the 14.01 and 14.001, when I'm 100th of a unit to the right, my y value is 1.0666. Okay. What about when I'm 1,000th of a unit to the right? No surprise, it added another 6 in there. So if I said, hey guys, what is f of 14.0001? You should automatically guess, well, I bet it's going to be 1.066666 and then 2225. So you're going to have 5 6s if you have 3 zeros. So you can say, well, clearly this number is approaching 1.06 repeating, which to 3 decimal places, which is, they wanted an answer to 3 decimal places on achieve, the 1.067. And you can see that's what I did there. Now for the next problem here, it gets into some trigonometry, which is always a cool thing. Let me go ahead and share my work with you on that one. Now, one thing I want to mention whenever we go to trigonometry like this, guys, please, please, please remember, whenever you're working with trig functions within problems, you cannot be in degree mode. Some of you are taking like engineering classes and stuff, and you may use trig functions in degree mode. In the calculus sequence, you will always, always want those trig functions to be in radians. So I need radian mode when I'm working with that. I go back to y equals, and I'll say, okay, well, I'm trying to find out what happens as x approaches 0, the sine of 9x over x. All right, so I know that it's undefined at 0 because dividing by 0 into anything is undefined. This is sine of 0 over 0, which is 0 over 0, undefined. Well, even though the function is undefined at 0, the limit's just asking, well, what's happening as you're approaching 0 from the right and left? In order to see that here, I'll say, well, it's the sine of 9x. And I could have chosen a fraction, but since my denominator was so simplistic, I just did use the division sign. So I have the sine of 9x. Please do remember to close out your angle divided by x. And then I can say, okay, in order to determine this limit, I would choose 2 values to the left and 2 values to the right. to the left, I'm going 1/100th of a unit to the left and 1,000th of a unit to the left. Then on the right-hand side, I do 1/100th of a unit to the right and 1/1000th of a unit to the right. I try to get closer in each direction. To show you how we would input that in here, and with 4, even on my lower resolution screen, I can fit them all in. And I'll go 0.01 and not negative, 0.001. So now, please notice, when I'm 1/100th of a unit to the left of 0, my y value is, and they asked us to round this to 5 decimal places here, I believe, in this problem. So I'll put 8.98785. And then when I went down to 1/1000th of a place to the left, you can see the pattern here is, wow, it added quite a few 9s in there. Instead of 8.98, it's 8.9998. So hypothetically, if I went to -1/10,000th, you should already know, hey, you're going to have an 8 point, and then you'll have 5 9s and an 8/7. Guaranteed. The pattern will hold. Now, on the other side, you have the 8.98785. Please notice whether it's negative or positive, it's the exact same value. This function is going to be symmetric with respect to the y-axis. It's an even function. And the reason is because actually the sign is an odd function, but x is also an odd function. Odd divided by odd creates an even function, and even functions are symmetric about not the origin, that would be odd, about the y-axis. I almost misspoke and said origin. And you can see the 0.00 gives us the exact same value as -0.001. So whether I'm approaching from the left or the right, either way, I can see the limiting value is 9. Gorgeous. Now, when I'm looking at number 8, I'll refrain from showing that on the calculator since it's the exact same type of problem, except, well, actually I will, because I want to show something that I see students do wrong. They might do like I did in the last one, sine of 4x. They'd close that out and then say divided by 3x. And then they'd say, well, hey, why am I getting a different answer on my calculator than what you got? Notice, they're still wanting to know what happens at 0, but these are not the values that you're supposed to be getting, although they are in scientific notation. My numbers are not supposed to be in scientific notation. Why are these? Why are these giving me bad values? Well, they're giving me bad values because I entered it in wrong. So you either need to use the fraction sign, the alpha y equals, or if you're going to have a denominator, if there's more than one term, you absolutely must put it inside of a parenthesis. And then you can go to your table of values and get the correct values in there. You can see the 1.332977, the next one, the 1.43s, and then all the way on down. When I'm looking at this, it was just asking, what is this approaching? And it wanted it rounded to 3 decimal places. And I can easily see this value is actually approaching 1.3 repeating, because I can see the closer I get to 0, the more 3s I'm going to have after the 1. So this value, it's actually approaching the fraction 4/3, 1.3 repeating. But since they wanted an answer to 3 decimal places, I just put the 1.333. Next one's similar. It gave me 3 cosine theta minus 3 over 2 theta. I found values of theta from the left, values of theta from the right. We were trying to find out what's the limit as theta approaches 0. So when I'm looking at my left-hand side, I can see that the closer I get to 0, the closer this y value is getting to 0. I can say, well, what happens if I go to -0.0001? I can already see it's going to be 0.4 zeros and then 7499. Does the same thing happen as you approach on the right-hand side? Absolutely. The terms are negative, but that's irrelevant, because these negative numbers are still getting closer and closer and closer to 0. So no matter whether I'm approaching from the left or from the right, the y values are approaching 0. That's my limiting value. Now, on the other hand, this next one here, it's wanting you to find the limit of this rational function, 1 over x minus 1 cubed, as x approaches 1. So I thought, well, if I'm approaching 1, I need to approach from the left, and I need to approach from the right. This is 1/100th of a unit to the left. This is 1/1000th of a unit to the left. At 0.99, my y value was -1,000,000. At 0.999, it was a -1,000,000,000. So that automatically told me, well, then the limit as x approaches 1 from the left of this function, and I showed this over here because this in and of itself would be a good question here. Instead of asking the overall limit, I could just say, what's the limit as x approaches 1 from the left of this function? And you'd say, well, clearly it's -infinity. What's the limit as x approaches 1 from the right of this function? Well, if you're 1/100th of a unit to the right at 1.01, the y value is 1,000,000. It's the exact same thing as here, except opposite sign. When you're 1,000th of a unit to the right, your y value is at 1,000,000,000. So you can say, well, okay, again, clearly, the closer that x gets to 1 from the right, the y value is going off to infinity. And so we would say, since the left-hand limit does not equal the right-hand limit, the overall limit does not exist. Please don't think that that limit doesn't exist because the limits are infinity. If these two had been the same answer, that answer would be infinity. So if this one had been infinity and that one would be infinity, that answer would be infinity. The reason this answer does not exist is because the left-hand limit does not match the right-hand limit. Now for the next problem here, again, we're just given a rational function. The limit as x approaches -10 of x plus 10 over x squared plus x minus 90. And again, they didn't give you specific values to plug in. Let me double check that just to make sure. I don't think they did. Oh, actually they did. I'm sorry. So the reason, and I was kind of suspecting that they might, because typically I would prefer just to do 2 to the left and 2 to the right. But the reason I did more than that this time is because they had you put all these function values in. So in number 11, they're wanting you to put f of -10.1, f of -10.01, f of -10.001. All of these should establish what the left-hand limit are. And then the right-hand limit, numbers to the right of -10, -9.9 is 0.10 or 0.1 of a unit to the right. This is 0.01 of a unit to the right, and this is 0.001 of a unit to the right. So when I'm looking at all of these values to see that I've done this right, I can say, well, as I plug in all of these values and I'm trying to think, what is this approaching? Well, from here to here, what's happening? I had 0.0523, here I have 0.0526. So this is not our standard pattern, but I can see, well, it went 0.0003 units more negative. So now I know that that amount of change is going to be lessened in the next one. So I went 0.05263. Now, so you'll notice it still went up just a little bit more negative, but instead of changing in the 4th decimal place, it changed in the 5th decimal place. So now, if I were to guess what's happening, what if I went to -10.0001? I would automatically guess, well, this number right here is probably going to jump up, and it's going to be like -0.0526. This number is probably going to go up 3, which is going to knock that number up. It's probably -0.052632. Now, there's no reason to even check that on the calculator, especially since we're only rounding this to 3 decimal places anyway. But you can see in the pattern, here the 4th decimal place increased. From here to here, the 5th decimal place increased. So in the next one, the only difference would be in the 6th decimal place. If I look at from -9.9 to -9.99, again, I see, well, what's happening? The 4th decimal place changed. It went from -0.0529 to -0.0526. So the 4th decimal place went down 0.3 of a unit. So now if I would guess what's going to be the pattern in the next one, I'd guess the 5th decimal place is going to go down 0.3 of a unit. And it didn't quite go down 0.3, but almost. It went down 0.00025, notice from 59 to 34, gorgeousness. So you can say, yep, that pattern is sort of still holding on. And I know that next unit would only affect the 6th decimal place. Is that going to affect the limit to 3 decimal place accuracy? You bet not. So you can just say, well, to 3 decimal places, whether we're approaching from the left-hand side or the right-hand side, we are 100% confident that that limiting value rounded to 3 decimal places is negative 0.053. Now that one, the pattern is not as obvious as it normally is, but there's still a pattern there. Now we look at some one-sided limits. With one-sided limits, you're only approaching the value from either the left or right. In this case, obviously from the right. So I could care less about values less than 4 here. I start off with a 1/10 of a unit to the right, then a 100th of a unit to the right, and then a 1,000th of a unit to the right. And as I plugged those in, I saw that the y value is just getting larger and larger and larger. And in fact, it more than multiplies by 10 each time. So for example, if I said, hey, what do you think the y value is going to be at 4.0001? It's going to be over 6,000. I guarantee it. It's going to be like negative 6,240 something. So I am 100% confident that as I get closer and closer and closer to an x value of 4, because of this pattern, the y value is going off to negative infinity. Now again, some students look at this and they say, how do you know it's going off to negative infinity? It's not necessarily the y values, but it's the pattern. I can say, well, every time I get closer and closer to 4 here, this value is going to be more than multiply itself by 10. So what's going to happen at 4 billion zeros and a 1? Well, clearly, if you multiply by 10 a billion times, you're going to go off to a number approaching negative infinity. Gorgeous stuff there. Now, what if we have a trig function times a trig function? No problem at all. Now, this one, it must have had a table of values, because otherwise I don't think I would have checked out so many. Let's see here, guys. For number 13, boom. Yeah, so the reason I listed so many was just because they asked for it. So we have the f of negative 0.01, negative f of negative 0.003. So I had to do all of these values, and they wanted those values rounded to, it said 6 decimal places. Make sure you're following the directions of what they want on the individual problem. So 6 decimal places, I just plugged these values into my functions, and I got this. Now, this should establish the left-hand limit. And I can see, well, as the values approach 0 from the left, it looks like the values, yes, they're going to oscillate, but despite that oscillation in the y value, those y values are getting closer and closer to 0. So the first one's positive, the second one's negative, the third one's positive. So I would expect them to continue to oscillate between positive and negative. But regardless of that, these values, the absolute value of them is getting smaller and smaller and smaller. And then I can see the same things happening over here. I had negative, well, actually, let me list this one first. The reason I listed them in this direction is because that's how they were on the page. But you'd really want to look at this one first and say, well, when I'm 100th of a unit away, I'm at negative 0.009. When I'm 1,000th of a unit of away, yes, it turned positive, but the absolute value of this number is 10 times smaller than this number because it's another decimal place over. And then similarly here, that number is smaller than this one. So you can say, well, the number gets smaller and smaller and smaller as x approaches 0. So I know that the limiting value is 0, whether I approach from the left or right-hand side. Looking at the next one, we have another trig limit. And this one, unlike the last one, is going to be undefined. And I need you to see why it's undefined. This is another one of those that I believe they ask you to plug in some specific values. Yes, f of positive or negative 0.1, f of positive or negative 0.01, and then f of positive or negative 0.001. So I just listed them on my table of values here. Now, Why can I put both of these together? Well, because the cosine function is an even function. F of x and f of negative x have the exact same y value. So that's why we can consolidate these two values and get the exact same y value. But now, unlike the last problem, why is this problem not going to go to 0? And this is a tricky problem. It's very tricky. And in fact, let me show you out. Just from what they asked us to do, to be honest, I would look at this and say, well, hey, I think it's approaching 0. It's not. Here's why it's not. So if I go in here and say the cosine of 5 over x here, I'll go to my table, I'll delete these out, do 0.1, 0.01, 0.001, 0.3 zeros, and a 1. Just from looking at this, I would almost make the same conclusion as the last problem, and you'd think, well, not sure, but it looks like the numbers are getting smaller and smaller and smaller. How do I know that that's not approaching 0? From the values that they gave you, honestly, I wouldn't know that they're not approaching 0. But what I did to kind of cheat the system, because I was suspicious. I was like, I think those should be getting even closer to 0 than that. I went 0.1, 2, 3, 4 zeros and a 1. So I said, well, what happens if you get really close to 0? That number should get really, really close to 0 as well if the limiting value is 0. But notice, boom, it jumped back up to a number near 1. So you're like, well, then that means that the limiting value is not 0. It's not. It's just going to continue to oscillate forever and ever and ever. So we can say, does not exist. Anytime the y value doesn't approach one specific number as x approaches the limiting value, there is no overall limit. So I said this does not exist because it's going to keep oscillating, or it will the function keeps oscillating between -1 and 1. The next one here, we had the limit as x approaches e of the rational function x minus e over the natural log of x to the 5th minus 5. Now, I'll go ahead and show this one on the calculator just because sometimes students aren't exactly sure what to do with functions like this when they're trying to find out what's happening at an irrational number like e or pi. It's really not bad, but we'll talk about it here. Make sure that that's as clear as it can be. There we go. I'll go ahead and put in my function. I would prefer to use the fraction and x minus e. The e button on your calculator, if you don't want it raised to a power, is best second divide, x minus e. Now my denominator here, the natural log of x to the 5th, x raised to the 5th. I'll close that out and then minus 5. Okay, I'll go second table, clear these out. And exactly how I have it entered in here is precisely what I did. You want to say, well, you need to establish a left-hand limit and a right-hand limit. So to establish the left-hand limit, I just said, well, how about 1/100th of a unit to the left, e minus 0.01. For the next one, I said e minus 0.001, and then e minus 0.0001. So I wanted to see if that y value is approaching some specific number as the x value approached e from the left. So please just use the e, and then if you're saying, well, if I'm 1/100th of a unit away, it's e minus 0.01, then e minus 0.001 for 1,000th of a unit to the left, and then a 10,000th of a unit to the left, you just literally enter in e minus 0.0001. And now you can see that the y values, they are all close together, and they are going to have a value that they're approaching. As that decimal gets 10 times closer each time by going 1/10th of a unit out, I can see the first one 0.5426, then 0.5433. So you say, well, from here to here, it increased about 0.000, and then, and actually I'm misreading that, it's 3.5, not 3. So it went up about approximately 0.0009. I'll say it went from 26 to 35 there. So 0.0009. Now, if I would try to guess, I'm thinking, well, it's going to go up again, but it's not going to be 0.000. It's going to be 0.4 zeros. 1, 2, 3, 4. And then please notice from 55 to 64, gorgeous, it went up 0.00009 units there. So you can say, well, then it's going to keep on going up barely, 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 but each time it goes up, it's another decimal place out. So it's not changing the value that much. And I can say, well, I'm already certain to 3 decimal place accuracy, that number's never, ever going to go above a 6. So we can say, well, to 3 decimal places, it's going to be positive 0.544, and I get that limiting value as x approaches e from the left. You can see here I did x approaches e from the right in a similar fashion, and I got that exact same limit. So since the limit from the left is equal to the limit from the right, the overall limit is 0.544. Gorgeous problem. And then if you want to think, hey, how can we get even more gorgeous than that? How about we look at inverse trigonometric functions? Nice. So with those, what I did here, oh, my calculator froze up. Bad. Here we go. It's like, I don't want to do an inverse trig function. Yes, calculator, yes, you do. We have an inverse tangent. You just do second tangent of 10x. We'll close that out, divide that by the inverse cosine of x. Gorgeous. And then we're trying to find out the limit, and if this is a one-sided limit, we're only interested in what happens as x approaches 1 from the left. So you'll notice here, I'll go to my table, delete out those values, and then you just say, well, if you're trying to find out what's happening as x approaches 1 from the left. Now notice I had to do quite a few values here because normally I would just do 0.9, 0.99, and 0.999. But honestly, I didn't really know from just those. So I kept going, and I said, well, what about 0.9999? And I can see, well, the closer I get to 1, the larger and larger and larger that value's going. Now, you could just come down here and say, well, what if you just did a whole bunch of 0.9s? Is that y value going to get super large? Of course it will. It's already, putting it in scientific notation, whenever you go in, that's, although you could have just said that's going to be 1,040,244. Guarantee you, the closer x gets to 1, the larger and larger and larger that y value is. In fact, every time you go out another 9, it looks like it's a little bit more than tripling in size. So you can say, well, clearly that y value, yeah, it's going off to infinity. For my next one here, we have 8 sine x over 7 absolute value of x. Let me go to my calculator just to make sure you see how to do the absolute value in there. I need to make absolutely sure you're comfortable with that. I'll go alpha y equals, put in the fraction. And we do 8 sine of x, 8 sine x. And then we'll divide that by 7. And then your absolute value, the best place to locate it is second catalog. And I always just use second because it's the very first thing on there. It doesn't stand for analog braking system, absolute value. And it'll either say ABS on the really old calculators and then put a parenthesis for you to put the X inside of, or the newer ones will go ahead and just put in the absolute value sign. So now we're trying to find the limit as x approaches 0 of this function. You can see now if I go second table and enter in the values that I had, I'll delete off my old values. If I'm trying to find 0 from the left, you'll see I started at 1/10 of a unit away on the left, so that's negative 0.1. Then I thought, well, I can probably see a pattern if I keep on going out another decimal place each time. So from negative 0.1 to negative 0.01, I can see, well, yeah, the y value didn't change a whole lot. I will be getting a pattern. And then negative 0.01. I keep on going like that. And you can see where I got all of these values in. And as I was doing this, I can say, well, from here to here, it got more negative by about 0.002. And then from here to here, I'm expecting it to get more negative by about 0.00002, and that's exactly what happened from 4 to 6 there. Now, whenever you're looking at this number, you might have that number memorized. I actually do. That is going to be 0.142857. 142857 is 1/7. So this is -1 1/7, or -8/7 as a fraction. Do you have to know the fractional answer? No, just because they only wanted you to round to 3 decimal places anyway. So to 3 decimal places, clearly this is going to be -1.143. Going next, we have another problem. Since I already showed this one with the absolute value, I won't show this one on the calculator. I'll just say if we had x minus the sine of the absolute value of x over 8x cubed, whenever you're entering these in, we're trying to approach 0 from the right. So I went 1/10 of a unit to the right, 100th of a unit to the right, 1,000th of a unit to the right, and then 1/10,000th of a unit to the right. You can see my y values kept on getting closer and closer to 0.020833. And in fact, they barely changed after the first one. I think Achieve wanted an answer to 4 decimal places here, or must have been actually 5, since that's what I circled. Let me make sure. For number 18. Yes, it wanted a final answer to 5 decimal places. So that's why I did that there. For number 19 here, pretty straightforward problem. It goes back to just a rational function, but it's wanting the limit as you're approaching -2 from the right. Please be careful with that. I see students make sign errors when they're approaching negative numbers. Remember, if you're approaching a negative number from the right, your number is less negative. So -1.9 is 1/10 of a unit to the right of -0.2. -1.99 is 100th of a unit to the right of -2. And then this is 1,000th of a unit to the right of -2. I saw as I plugged those numbers in, my y value is going to get multiplied by approximately 10 each time. So I can say, well, then the closer this x value gets to -2 on the right-hand side, clearly that y value is going off to infinity, because it's just going to keep getting larger and larger and larger. Now, the last two were just graphs that you looked at, so they didn't really have any work to show. I just put their answers there. Let me pull them up here. When I'm looking at this one, it says determine the one-sided limit of the function f if the figure, in the figure at the given point. So I'm supposed to find in my problem the limit as x approaches a from the right. So I say, well, all right, I go up to my function. Here's a. As I approach a from the right, clearly that y value is going up to positive infinity. Anytime you approach an asymptote, the y value has to go to positive or negative infinity. And in this case, when you're approaching a from the right-hand side, you're going to positive infinity. So no question about that one. For 21, it gives me another graph. And my question asked, what is the limit as x approaches 1 from the left of f of x? So right here is x equals 1. As I approach 1 from the left-hand side, I can see that that y value here, it's approaching a y value of 3. And in fact, the function is continuous here, which means the limit from the left and the limit from the right as x approaches 1, it's the exact same thing. It could ask, what's the limit as x approaches 1? Your answer would still be 3. So this left-hand limit is the same answer as the right-hand limit or the overall limit as x approaches 1, just a y value of 3. All right, guys, hopefully that helped out with this section. Let me know if you have any questions.